Okay, so just a bit more about catalysts. I think we've mentioned this before. You've got heterogeneous catalysts and you've got homogeneous catalysts. A heterogeneous are your classic catalytic converter in a car or contact process. Think about the catalyst of the contact process, Haber process. You know what they are. They take the reactants onto the surface of the catalyst. They weaken the bonds in the reactants, and that gives the reactants a chance to react, form the products, and then the products leave. Okay? So this, heterogeneous because they're in different phases or states. Typically solid with a liquid or gaseous reactant, but yeah, you know those examples. There are active sites on the catalyst, so places where the reactant molecules can attach. Active sites, they're called. And these reactants are adsorbed onto the surface. It's just a superficial thing. They're adsorbed onto the surface. Their bonds are weakened by this adsorption process. It brings the reactants closer together on the surface, and therefore they can weaken the bonds, they can react with each other, they can form the product, and then the product is desorbed from the surface. So it leaves the surface. Okay. Why are heterogeneous catalysts so important to the chemical industry? Well, obviously catalysts, they lower the temperature, they improve the efficiency of the process because it costs less to make the chemicals, fewer byproducts, etc., etc. There's lots of reasons why catalysts are so important. It's about cost. It can also be to do with the environment. They can avoid the production of toxic materials, improve atom economy, etc., etc. Okay. Homogeneous catalysts are catalysts in the same phase or state. Now, when I say phase, imagine in solution. So you could have a catalyst in solution, which is dissolved in a solution. So cobalt ions, for example, might catalyze a reaction in solution. And in the end, they remain in solution. Okay, so they're in the same phase. The other classic example is the ozone layer and chlorofluorocarbons, CFCs. So the chlorine radicals, which we've mentioned before, were very good at breaking up the ozone, destroying the ozone. It's getting better. This looks a little bit depressing now, but it's definitely getting better because the CFCs were banned in the 80s. And for once, everybody took note, well, almost everybody. And essentially, the production of chlorine radicals has rapidly decreased, but they're still getting up there somehow. We've talked about that reaction before. I think so we'll be okay there. Now, just a little look at this. This is potentially a homogeneous catalyst working. You've got the reactants and the products. The homogeneous catalyst can react with the reactants to produce this intermediate, and that intermediate reacts with more of the reactants to produce the products. Don't worry too much about it. But the point is this, look, if you look at the activation energy of the reaction without the catalyst and with the catalyst, then there are two small activation energies. So the reactant particles have got enough energy to overcome both of these humps to make the products. So remember, it's an alternative route with lower activation energies. And that's that. You can watch these two videos from YouTube, and we'll have a little chat about some of these things in class.